Recording right now. It seems like we can just share our screen. Okay. Beautiful. I think it's working now. Okay. We can start.
Yep. So we're just going to go through a couple of problems, and feel free to stop us at any time to ask us questions, or if you have your own questions, feel free to ask them. So here we have a branches and nodes problem. Just the main thing is remember the definition. So a node, it's a point of connection between two or more branches. And a branch is a single element. So that can be a voltage source or a resistor, for example. And a loop is just any closed independent path. So there are a couple of options to do this, but I would suggest just by counting how many nodes we have, which again is a point of connection between two or more branches. So here we have a node. We have a node in here as well because we have these three elements. And then we have a node here and a node here as well, where we have branches here that connect. So that gives us 4 nodes. Now to find the number of branches, we could just count them as these, since these are single elements. Or another option is we can first count the number of independent loops, which means that they don't have any inside loops inside. So in our case, our number of loops is equal to 3. We are not going to include a bigger loop since that's not independent. And then you all might have seen an equation where the number of branches is equal to nodes plus loops minus 1. So then we just plug in what we have. That's 4 nodes, 3 loops minus 1, which should give us the same answer, 6 branches. Hopefully this makes sense. Please let me know if you all have any questions. All right, I'll move on to the next one. So here, I feel like this is actually a really important concept, like knowing your KVL and KCL, because once you know that, a lot of the questions are pretty approachable. So for here, this is just a simple KVL problem. We are supposed to find R, and we have V equals 20 volts. So just be sure you follow around in a loop and pay attention to the signs. So if we start here, this will be negative 20 volts. And then remember Ohm's law, where voltage is equal to current times resistance. So here, we can still say it's 10 volts. For here, there's a current flowing through it, so we can say plus 10I. And then finally, we have this voltage here, where you start with a negative, so that's a minus 30 volts. And we set these all to 0. So from here, you can just solve for I. Which should give you 4 amps. So once you know what I is, they're asking you for what R is. So again, this is Ohm's law. We have 10 volts, we have 4 amps, and we have R. So from there, we can just solve for R, which should give us 2.5 ohms. Does anyone have any questions over KVL? All right. Okay. I believe someone asked why is it minus 20 volts. That just depends on where you start, like you can choose your current direction. Here I'm choosing I as clockwise. So when you go clockwise, you see that we are starting from the negative. So it will be negative 20 volts. Yeah. So if you made I going the other way, that's totally fine. You would just need to switch the signs. So here it's a bit more of a trickier problem, but just try to apply the concepts, find what you know. So for here, it's asking for the current, voltage, and power for R, which is 26 kiloohms. So one way we can start, we see this VO over here. We can find what we, or VO or V out, we can find out what that is. And for that, we can use Ohm's law because we have the current and we have resistance. So we can say that VO is equal to 5 milliamps times 10 kiloohms, which just be sure you pay attention to the units, but that should equal 50 volts. And then here we have a dependent current source, which is 0.01 VO. That, if you plug in 50 volts, it should give you 0.5 amps. So now here, if we wanted to find information about the 26 kilo ohm resistor, you would have to use current division, where some of you may have learned the equation. That is totally fine to use. I personally would just try to realize that both resistors are in parallel, find the voltage, and you can use the voltage to solve for the current. So this is how I would do it. We have the 5 kilo ohms and the 26 kilo ohms in parallel. So if we combine those, that should give us 4.193 kilo ohms. That is your combined resistance in parallel. And now since we have the current 0.5 amps and the resistance, we can find V total, which is equal to 4.193 kilo ohms times 0.5 amps. That is equal to 2.0967 kilovolts. So from here, here's the really important part to remember. When you have two, like anything which is in parallel, the voltage for the equivalent resistance is the same as the voltage for each resistance. So basically the voltage for the 26 kilo ohms, it is the same as what we just found here, V total. So we already found one of the answers. Now to find the current, we can again just use Ohm's law because we have the voltage and we have the resistance, which is 26 kilo ohms. So solving for I, we should get 0.0806 amps. Then finally for power, power is just equal to voltage times current. So just using the two values we have, we just multiply them. And that should give us 0.169 kilovolts. Does anyone have any questions over this? All right. I think we should be good. So the main thing is like even when you see things like current division, like even if you don't remember the formula, that's okay. Just see. Usually the resistors will be in parallel. Find the total voltage, and knowing that the voltage is the same for each resistor, you can find the current as well using Ohm's law. And in these kind of problems, just try to find out the information which you know and then use that. Because here we had a dependent current source. So from there, we were able to figure out the total voltage. So,
Okay, so next we have a resistor network here, and we're trying to find the equivalent resistance, and then afterwards we need to find the current. So with problems like these, I think it's easiest to start off away from the voltage source or the power source, whatever you have. So I would start off on this side of the circuit just because I think it's easier to work your way in. So right off the bat, when I look at this, I see that this resistor right here and this resistor right here, the 20 ohms and the 80 ohms, are in parallel with each other. So what I will do is I will combine them using what we know about parallel resistor combinations. So here, what we need to do is we need to do the reciprocal of each of these when we're adding them because they're in parallel. So this would be, this equivalent resistance would be 1 over 20 plus 1 over 80. And this is equal to 16 ohms. If you are on a time crunch and if you're trying to plug this into your calculator, I think it's easier to just do 20 times 80 over 20 plus 80 for these parallel ones, just because it's faster and it's a more foolproof way of putting this into your calculator so you don't accidentally make a mistake. So now that we got the equivalent resistance for these two resistors here, let's go ahead and redraw this circuit just so it's easier to visualize what we have. So this plus or minus 35 volts. Then we have this resistor here. Then we have the 15 ohms. And then we have the 6 ohm resistor here, the 12 ohm here. And then here is where we put the new resistor that we have, which is the combination of the 20 and the 80 ohms. So after this, we have this last one here, the 60 ohms. And this is what our circuit becomes after combining those two. So now what we do next is we look for the next combination that we can do. And here I'll combine the 12 and the 6 because they share these nodes here. Oops, and again, these two are parallel with each other. So again, we combine them. I'll just write 12 and 6 like this for those two resistors. So we have 1 over 12 plus 1 over 6, which is equal to 4 ohms. Again, let's redraw this so we can visualize. We have the 16 here from before, and then we have this branch with this resistor here. So as you guys can see, we combined this 12 here and this 6 here, and it became this 4 that we have right here. So next, we can see that the 4 ohm resistor, this one, and the 16 ohm resistor are in series with each other because the current going through here goes directly down like this. So we just add those using basic addition. So we get 20 ohms for that. Again, redrawing, we get the following circuit. I think if you guys are just, learning this and you're trying to get used to it, I think it's best to redraw after each point just to make sure you're visualizing everything correctly so you don't make any little mistakes because, you won't have, you're not allowed to make mistakes on the exam. But eventually, when you get used to doing a bunch of these problems, you'll get used to doing these without having to redraw after each point. Anyways, moving on, now we have this 20 here and the 60 here, which are parallel to each other. So again, we combine those with each other. So it would be Let's do R20, R60. Also, these are all similar notations. Like this is like a similar notation. This, like the R just means the resistor, and then the number is which resistor we're combining. So you guys can write it either way, whatever works best for you. So combining this, we get 1 over 20 plus 1 over 60, and this is equal to 15 ohms, 1, 5. Drawing, we get this 4.8 here. Then we have the 15 ohms. And then this new resistor that we have here, which we just solved for. So as you guys can see, when you're working it like slowly like this, it's easy to visualize and easy to actually solve these. They're not that difficult questions. Next, this 15 here and this 15 here are parallel, so we do those two. So we get this, and this is equal to 7.5 ohms. Redrawing, we get this, 4.8, and then we have the 7.5 here that we just solved for. Here we have these two resistors in series with each other because the current coming out from here is going through both of these resistors equally. So we just add those together like normal. We don't do the reciprocal. And we get 12.3 ohms, and this is our equivalent resistance. Any questions so far before we move on to the current? Okay, so someone said the formula you used of 80, 20, 80 plus 20 only works. Yeah, it's only for two resistors in parallel. That doesn't work for anything else. And it looks like Josphin answered that. Any other questions before we solve for the current? Okay. If you guys do, you can just write it in the chat. So now to find the current, we just use Ohm's law. So V equals IR. We rearrange this so we have I equals V over R. Our V here is the 35 volts, so we put that on the numerator, and the denominator is the equivalent resistance that we just found. So we divide by 12.3 ohms, and this will give you 2.85 amps. So this source right here is giving off 2.85 amps of current, and that's basically this question done. Any questions? Okay, I don't think we have any, so I'll move on. We'll skip this one for now because we have another friend who is supposed to solve this, so I'll just move on to the next one, which is on phasors. Also, before I move on, I just want to make a quick note. In this session that we're doing here, we're mostly just solving problems that you could possibly see on the exam. But if you guys have issues with like the actual fundamental concepts and you don't understand those, then you guys can go ahead and watch the ieeeut 1202 videos from past years, like last year's video, for example. The tutors there actually explain the concepts as well. So if you don't understand the concept like as a whole, then go watch those. But if you just need some extra practice, then this would be more helpful for you. Okay. So now we'll do this phasor question here. So here we're asked to find the simplified form of the function g of t, which is what we have here. So let's just rewrite that so it's more clear. And we just want to simplify this, so it's nothing too crazy. So this is what we have for, where are those videos? They're on YouTube. So if you go onto ieeeutd, I think that's what the channel is called. They're all posted there. There's like the videos from last semester and like the other semesters before that are all uploaded, so you can just watch them there. That's how I studied for these exams when I was taking this class, and they were very helpful. If you guys have like more questions as well after this session that we're doing, you can come find us at IEEE whenever. I mean, we have our tutoring hours posted on the Discord, so you can check that out. Okay, so let's go back to this question. So we have this function, g of t. We need to convert this, or just simplify it. So to do that, we first need to convert this sine of t right here into cosine, because we can't add these if they have different like sines and cosines. So to do that, it's very simple. So let's say convert sine of t to cosine of t. So here you just subtract 90 degrees from what we have inside. So this would be 7 sine of t is equal to 7 cosine t minus 90 degrees. So now we have this function, the first part of the function, in terms of cosine. So now we can add these together. So let's just rewrite this real quick. 7 cosine t minus 90 degrees plus 4 cosine t plus 50 degrees. So recall that you can't add and subtract these values in polar form. We need to convert this into rectangular. So first, right off the bat, when we look at this, we can get the polar form of each of these, which is very simple. So for this first one, you just look at 7, and then you look at the degree, which is negative 90 degrees, and that's what this would simplify to. And then we look at this right here, this 4 goes here, and then the 50 degrees is like this on the right side. So this right here is this function in polar form. But again, we need to turn this into rectangular so we can add and subtract them. In polar form, you can only multiply and divide in the scope of this class. So to convert the 7 with the negative 90 degrees, we need to make this so it's an x plus jy form. So to do this, we do x is equal to 7 cosine negative 90. And this is the formula for this. So if you don't know this formula, then definitely learn this. So to convert to y, we use sine, and then to convert to x, we use cosine. So we get 0 for this, and we get negative 7 for this. So this function becomes 0 minus j7. Any questions so far? Okay. Give me 1 second. There's someone at the door. Okay, so moving on. Now let's convert the 4 with the 50 degrees. So again, here we want this in x plus jy form. So again, we do x is equal to 4 cosine 50. And then we do y is equal to 4 sine 50. So simplifying these two, we get 2.57 for x, and we get 3.06 for y. So this function here becomes 2.57 plus j 3.06. Okay, so now we can add these together. So we get g of t is equal to 0 minus j7 plus 2.57 plus j 3.06. Remember, we can only add this component with this one and this one with this one. So adding this, we get 2.57 minus j 3.94. And now looking at the question, it wants it in the form that we had originally. So we have to convert this back into Phasor. So to do this, we do r is equal to, you take the x component, which is 2.57, and you square that. And then you take the y component, which is negative 3.94, and you square that as well. And then you find the square root of this, which is equal to 4.70. And to find the angle, you do arctangent y over x, so it would be negative 3.94 over 2.57, so the y over x, and then you get negative 56.88 degrees. So your simplified function becomes g of t is equal to 4.70 cosine t minus 56.88. A key note here is that when you're converting these and you're trying to find the angle like we did here, when you put this into a calculator, sometimes what happens is that, for example, if you have a negative and a negative, it'll change your value. So a negative and a negative here, it would change your value into a positive, and it might give you the wrong angle. So definitely look at which quadrant you would be in and see if the angle that the calculator gives you is correct or not. But yeah, that's what this answer simplifies too. Does anyone have any questions before we move on? Okay, great. In that case, I skipped question 5, which was the voltage one. Do you want to do that one now, or do you want to? Okay. Here you go.
Let's do it and talk it through. Okay. So with this question, what you do.
Oh wait, someone raised their hand.
Oh.
Sorry. E unverified. That's what your name says. Your hand is raised. Do you have a question? Okay, maybe you did that on accident.
So for this, you were taking the voltage division.
Wait, I'm so sorry. He did actually write something just now.
Oh.
Do we do 360 minus 56 to get 303.12? What question is this for? 360 minus 56. Wait, do you mean for the angle? Oh. I mean, usually they'll give you like a range. For the last one, did we have to do something with the negative value? Yes, for the angle. For this one specifically, I was able to just put this into the calculator and it gave me the right answer. But sometimes with certain values, it won't do that. So just think it through, like think about your answer and see if it makes sense. Here it says the range for the angle is from 180 degrees to positive 180 degrees, so you wouldn't be able to put 303.12 because that's out of the range that this question is asking for. No problem, you're welcome. Go ahead.
Okay. So, okay, for the voltage division, you have to find R2 first, which you can find the value of R2 based off of the VD off of that formula, off of this formula, which comes from VD equals R over R of, like, for this would be 2. And actually, no, we don't want to do that way. Actually, yes, we do. We do want to do it that way. We can find BD of R2 over current total. And we can find current total by summing the 2. So, but we can't do that just yet. So 10 equals I times R1 plus R2, because they're in series. So we can find the value of R2 by finding the difference in the voltage. So 10 minus 7. So there's a 3 voltage drop of 3 at R3. A voltage drop of 3 volts off R1. So the VD of R1 is equal to 3 volts. So we can use that same formula from up there of 3 equals R1 of IT to find IT. And R1 has a value of 5.5 kilo ohms. So 5.5. So we can take the inverse. So it's 1 over 3 equals IT over 5. And that gives us the value of IT, which is over 3. So now we can substitute that in to find the voltage drop of R2. So we can find the value of R2. Actually, no, we can calculate that just by, it's 7. Yeah. So 7 of R2 over, and it's 7 because that node, the negative node right here has to be 0. So we know that if this is 7 volts here, if this is a 7 volt difference, voltage, like potential difference, and it goes to 0 potential through this resistor. So it's just 7 minus x equals 0, which is going to equal -7, but in this case it's going to be 7. So we'll use the positive value of it because that's how the formula gives the answer. So next, what we're going to do is we're going to solve for this, which is just 7 times over 3 equals the value of R2, which roughly turns into turns into this value in ohms for the value of R2. So that solves question 1 of this part. So we know that R2 now equals that. And I'm going to have to erase. Okay, so now we can start this part. If we're given R2 and 20 volts, so the power supply is now 20, and we're given R2, and we need to find V2, but we know the value of the total of all the resistors. So what we're going to do is we're just going to add R2 and R3, and R3 is given as 8 kilo ohms plus the value of R2 times total current equal 20. So that leaves us with 20 over yeah, equals our I of t, which is 960 microohms, or amps, sorry. And given this, we can calculate the voltage drop of R2. So what we're going to do here is that VD equals the value of R2 over total current, which equals over that's not right. It's not right about that. What we're gonna do now, did I not send that right? Something was not right. Maybe something. So we're gonna take 20 over and then that's going to be equal to IT, and that we know VD is equal to IT over R of 1, which could be any resistor. And so what we're left with is okay. They use long formula. They use long formula.
I think you used the wrong formula.
Okay. Well,
You found the right resistor value, R1, and then it's just voltage division across R2.
Okay. Yeah. Okay. Yeah. Okay.
So you don't need to solve for current.
Okay. Yeah. That makes more sense. Yeah. So you don't have to solve for current actually. Like this. So to find the voltage drop, the voltage is going to be okay. So it's VS times the resistor we're solving for plus times the sum of not R1, R2 plus R3. Okay. Yeah. Okay. So basically, with this, let's substitute the values in. We know the value of R2, which is 12 point. 8,000. Okay. No, I did the wrong sign. Yeah. Okay. So now you just put those numbers in. Which gives you the value of 12.832 for V2. So V2 is equal to 12.32. Okay. So now that we know V2, we can go to the next step.
Give me the eraser picker.
No, it's fine. Now we have to find the value of R4. So we know that the voltage drop across that is 12. No, we know that. Actually, yes, we do know that. I think, yeah. So the value of this node is going to be 20 minus 12.32, which equals 7.78. Let me check real quick, actually. No, 6.8. Yeah. Good thing I checked. Both. So what we can do now is that we find the value of R2 by knowing that the value of R3 is 8. We'll go ahead and R3. R3 equals 8,000. We can take the voltage of we need the voltage of our V3, which is going to be, this will be V3, which has that value. So we have 7.68 multiplied by the resistance of R3, which we know is 8,000, divided by voltage supply, the supplied voltage, minus the voltage of V3, which equals, and this will give the value for R4, which equals 4.9. Okay. So with that problem, we have the answer. Is there any questions about it? Oh, no. Yeah. We're good. Anybody? Okay.
Is there a question? Someone asked a question. What is the 20 over 7.68? What is it dividing?
The 20 is the voltage source over 7.6 point. So 20 is the voltage source. So it's Vs over V3. And V3 is
He said thank you. Next up, we have another Phasor problem. So this is the one that we just did, and then we have this one here. So looking at this question off the bat, we're given a phasor and we're trying to find the sinusoid for that phasor. So this is the phasor that we have, and we want it in this cosine sinusoid function. So what I would do is I would write this cosine equation, the one for the sinusoid, which is in the time domain. So it would be I2 of t is equal to I2 cosine omega t plus theta. So we're given omega right here. So that's just a matter of plugging this in. So it's 998 radians per second. And if you guys remember from the previous phasor question, we need to convert rectangular into polar so that we can easily implement it into this equation here. So we take I2, which is in rectangular form right now, and it's given as negative 0.5 minus j 1.2. amps, and we need to convert this into polar form. So again, to do that, we do R is equal to, we do the x component squared, so negative 0.5 squared. Then we do the y component squared, which is negative 1.2 squared. We add those up and then find the square root, and that equals 1.3. We don't actually need to solve for the angle in this because we're already given it. So this is actually all you need for this question. It's very easy. And then if you were to just rewrite it, you would do I2 of t is equal to this value right here, 1.3, cosine. We use the given value here, which is 998, and then we do, and this is multiplied by t, and then we subtract minus 112.6 degrees, which is already given in the question here. And this is what this phasor is equal to in sinusoid function, or the sinusoid function. Does that make sense? It's a very straightforward and actually like easy question. It doesn't require a lot of math or anything. You just have to think it through a little bit. Okay, moving on then.
Alright, so our next question is about combining capacitors, and I might just do a quick review of a series and parallel, because one thing you should remember is capacitors, they are not the same thing as resistors and inductors. So like, as a quick way to remember, for resistors and inductors, when you're doing series, you just add them up. So that can be also like L1 plus L2 if you're doing inductors. And if it's parallel, yeah, a couple ways to approach it, but personally this is the easiest one. Just do this for as many as they are, and this is the same thing with inductors as well. But for capacitors, it's just best to remember that you sort of flip them. So for series, you actually do this, and for parallel, you would add them up. So just, if there's like one thing you should be able to memorize, just memorize this, that capacitors, they are not the same. You don't combine them the same way as resistors and inductors. You instead sort of flip the way you do it. So onto the problem. We know that this one is 21 microfarads, and they're just asking us to find the equivalent capacitance. So when you're looking for in parallel, which is just in general, we just look for more than one way to connect them. So like for the left-hand side, you can connect these two like here, and also from here, so that makes them parallel. And same for like these two, connect them here and here. So that actually makes all three of those parallel. For this kind of problem, I would recommend combining two at a time though, just so to avoid confusion. So we can start from the bottom, like these two are in parallel. So remember, for capacitors, you just add them. So that should give you 50 microfarads. And then we had this, like this A thing. That will move up here because since we're like sharing the node, we would move it accordingly. We still have the 10 microfarads. Let's see. And I'll go ahead and combine these as well. They are also both in parallel. So again, we just add them. And likewise, we have this, so they just share the node. We have to move them. And then this is like what you would get. So now we can also combine these two in parallel and these two in parallel. It's like the same thing. So that at the end, so you would add 10 plus 50, that's 60. And likewise, we add the 10 and 20. Yeah, so I drew this one more. And yeah, again, move that here. So now we notice that these three are in series. We can't say that C is in series with them because we still have this. And remember, for series, they can only be like one, the node cannot be shared by anything else. And here, because of the A and B, the node is being shared. So C is not in series with these three. So just remember that, be careful about it. So if we were to combine these three capacitors in series, that should give us 10 microfarads. So we have C, we have 10. And now the final step is we notice C and 10 are in parallel. So again, we just add them up. I believe C is 21 UF plus 10 microfarads. So our final answer would be 31 microfarads. So hopefully this makes sense. Just remember, for combining capacitors, you try to think opposite than what do you do for a resistor or an inductor. And be sure you keep track of the nodes to ensure you don't mix up the series and parallel. So does anyone have any questions before we move on? All right. Okay.
So with this question, it can give you, it's nice and awful. Well, it could be terrible, but since this doesn't have a resistance value, or so let me draw that. So capacitors and DC conditions, remember, don't or have a resistance value that is approaching. Just let's say it's like limit of R go to infinity under DC conditions, because there's no, it's an open circuit, so is R of because they technically do have resistance. Yeah, but that means that this resistor right here doesn't impede the voltage at all, because it's 1 over 50 of 1 over infinity to the negative first, which no current is going through. So what that means is that the voltage of this point right here is equal to this point. They haven't done op amps yet, have they? Okay. So the voltage of those 2 points is equal. So really we can just ignore that resistor, because we could, and it'd be terrible. Well, not terrible, but not as fun. So they're asking us for the voltage at V1, which is going to be the voltage from those 2 points. So So what we're gonna do is we're given R2. Okay, so if R2 equals 11, and so we have to calculate the resistance of this loop. And pretty much all that capacitor is saying is that we have V1s from here to here. So, because the capacitor doesn't mean anything because it's an open circuit. It's there solely to confuse you. But then we take the R1, which is equal to 72 ohms, and then we have to add. We'll just call this R3, just to make it not as more uniform. So that's 10 ohms. So the total resistance of that whole node is going to be 93 ohms. To find the current of that node, we use the V equal IR formula. And V is 60. So I times 93 will equal 0.65 amps. Okay, and now I can use the voltage drop formula. So to find V1, it is the drop of R2 right here and then R3. So what we do is we take the sum of those two values, which is 72. Oh no, we don't take the sum actually. No, we take 72 over over the current. Yeah, that's defined. Yeah, okay. So we take the 72 over the current we just found, which results in 46.45 volts for V1. And that would be the voltage across this point and that point. So to find V2, what we do is we take the current, the voltage supply, and then subtract it by the resistance of R2 right there. So 11 divided by our total current going through that node, or loop, sorry, which gives us the value of 52.90 volts between right here and right here. So that's your plus, that's your minus. Okay, any question?
Are there any questions, Josphin? In the chat?
Yeah, I think somebody asked a question, but it's a way different.
Is this for a different question?
Yeah.
Okay.
Phasor.
Wait, there was a question. Can you open the chat?
Yeah.
Because someone asked.
Oh yeah, somebody.
Why did we do R1 for V1 and not R3 and R2? Do you want to take a look at that, David?
So for V1, you didn't do R1 and R2 because it's easier to go from the negative side than it is from the positive side. So we went backwards. Oh, okay. So instead of going how the loop is shown, essentially we did some funny math to go that way. You see how in V1 we had to do subtraction? No, V2, sorry. V2 we had to subtract by the voltage supply. So basically for V1, we did it backwards. Because that's the voltage of the node that we came from, which is this node right here. And then we found what it should be here using this side as our voltage source. Oh, yeah. Does that make sense? Everything makes sense.
I get it now. So.
Okay.
Thank you. Okay, so next up we have a energy question. So there's two versions of these questions. One is with a capacitor and one is with an inductor. So these formulas up here are each of the formulas for those. So if you have, if you're being asked for energy in a capacitor, you use 1/2 equals CV squared. And if you're being asked for an inductor, then you use 1/2 Li squared. Here, C is the capacitor, V is voltage, L is the inductor, and I is the current. I is not inductor in this case, it's current. So make sure you keep that in mind. So looking at this, we're given this circuit, we have a capacitor here, and we can just disregard the resistor because we're being asked for the energy stored in the capacitor. So the resistor doesn't really play any part here. So our capacitor value is 1 farad. So we're given different times and we need to find the energy and the capacitor at those different times. So for t is less than 0, what we do is we look at this function that we're given here. So we have the voltage function and there are 3 possibilities that we can have depending on the range for the time. So when it says t is less than 0, we would look at this first part right here because t is less than 0 here. So for the voltage, we use 0 because that's what we're given. So we do W is equal to, or it could be E, they're all the same thing. Let's actually just do E because energy, it might be more clear that way. So we do 1/2 is equal to CV squared, which is 1/2 times 1, which is this value right here, the value of the capacitor. And then we do 0 for the voltage. And so for this one, we get 0 joules for the first answer, for the first question. So moving on to the next one, now we're being asked for the energy when we're between 0 and 9 seconds. That's the time domain that we're given. So we look here at this function again, and that's this part right here. Here we have 3t for voltage. So again, we just plug this in to our formula. So we get E is equal to 1/2 times 1 because of the capacitor again. And then for voltage, we have 3t, and that's squared. So when we simplify this, we get 1/2 times 9t squared. Here the question is asking the energy stored is blank t to the power of x. In this case, x would be equal to 2 because that's the exponent that we have. And the energy would be 9/2. So it would be 4.5 with x equals 2 joules for the second part. Now we're given an actual value instead of a range. So we're given that t is equal to 7 seconds. So we look at when t is equal to 7 seconds, and that falls in this range here, the range that we just used. So again, we're looking at the 0 to t is less than, from 0 to 9 seconds for t. Here again, we're going to use 3t, but this time we actually have a value for t that we can plug in. So what we get is E is equal to 1/2 times the capacitor value times 3 times 7. Again, the 3 comes from this function here, and then the 7 is what we're given. So we multiply those and we square them. So from this, we would get 1/2 21 squared, which is equal to 220.5 joules. For the last part, we're given t is equal to 10 seconds right here. And that falls in this range here. So now we're using this last range. Here the voltage is equal to 27. Because we're given a solid number, we don't plug in 10 into the voltage. We use 27. So for this one, we get T is equal to 10. We're looking at the range where T is between 9 and infinity. And this is just a value that's given. So here we do E is equal to 1/2 times 1, the capacitor value, and we do 27 squared, and this is equal to 364.5 joules. So basically, for questions like these, first you have to remember these formulas here, and then afterwards you just have to take a step by step and look at each range and see where you fall between them. Any questions? Okay, and this will very highly likely be on your exam, like a question like this, so make sure you know how to do these. Yeah. Next we have
So here this is just a more complex version of voltage division, and I would brush up on your complex numbers because you'll be using that a lot. So a good way to set this up, all of these are in series, like the elements. So because of that, it's the same current going through them. So we have Vs equals I times Z equals. So now they have given us Vs, but let's try to find what Z equals is first, the total impedance. So that, because the elements are in series, you just add them up. So that's Zc plus Zr plus Cl. Now for the impedance of the capacitor, this is where you just have to remember stuff. For that, for Zc, it is just, you might have heard of either minus J over Wc. That can also be written as 1 over JWC. It's just because when you have a negative J, you can flip where it is. So I would prefer writing it down like this. ZR is just the value of R. And for ZL, for the inductor, that's just JWL. So now this is where we do have to use our complex numbers. So first start with plugging in what we do know. So for W, we can go towards the voltage. And we notice the 5 here. The 5 is the value of W. For C, they have given it to us, that's 0.2. For R, we have 1.5 ohms. And here, the inductance is 0.1. So now here, you really just have to be careful over the signs. So what I would do, there are a couple of ways to approach this. You can just remember that you can divide 1 by 5 times 0.2. And remember, 1 over j is the same as negative j. So if we do 1 divided by if you do 1 divided by 5 times 0.2, that's just 1 plus 1.5 plus j times 5 times 0.1, that is 0.5. So now here we can just combine like terms. That's 1.5 minus 1 plus 0.5, that's minus 0.5. So we have the rectangular form of z equals, and we can put that down as one of our answers. So here it's asking in rectangular form, just that's 1.5, negative 0.5. Now it's asking us to convert to Phasor, which anyway is going to be useful because we'll be doing a lot of multiplying and dividing. And for that, you want to convert to Phasor and not try to do it when it's rectangular. So to convert to Phasor, remember this. So this is x, this is y. That will be negative 0.5. So to find r, that's the first value you see. That's the square root of x squared plus y squared. Because just remember, x squared plus y squared equals r squared, the equation of the circle. So from here, we can plug in what we have. And using the calculator, that should give us 1.58. So that's the value of r. Now it's asking for the angle. So the angle is always going to be arctan of y over x. Now this is again where I would highly suggest for you to be careful. You can just plug this into the calculator. It may or may not be the correct value, especially when there are negative signs involved. What I would do first is plot this out. So it's 1.5x and it's a negative 0.5y. So it should be in this quadrant. So just ensure that whatever angle you find, it makes sense. And usually it always expects it between negative 180 to 180 degrees. Just be sure to check that. So for this, one way we could approach it is we have like a positive angle. And I know it's like in a different quadrant, but if we had this positive angle and our actual angle is over here, that this is just a negative version of that. So we could just say it is negative arctan of use positive values only, 0.5 over 1.5. So plugging that in, that should give us negative 18.434 degrees. So I believe when entering this increment, yeah, you can just enter it with the negative sign. You could also just plug this also in a calculator with the like arctan of negative 0.5 or 1.5. But just be sure and check if your answer makes sense. That is the main thing to remember. And if there's no harm in drawing it out, plotting it, check which quadrant it's in. So whichever way you choose, be sure you check the angle when using arctan. So now that we found Z equals, we can find the voltage across the capacitor. So here we are going back to voltage division. So we set an expression for I. So I is equal to Vs over Z equals. So for Vs, it gives us in Phasor format 2 cosine of 5t. So that is just the same thing as saying 2 at an angle of 0 degrees over Z equals, which we got it as 1.5 over negative 18.43 degrees. To find the voltage across the capacitor, that will be just I times the impedance of the capacitor. So again, it's just really a lot of math. Keep track of your signs. Let's see. So for the voltage across so we did find ZC over here. That was negative J times 1. It was negative J. So that is the same thing as 1 with an angle of negative 90 degrees. Just remember, positive J is 90 degrees, negative J is negative 90. So if we can just use this, so it's going to write over here, VC is equal to, this is I, and we have ZC, so that's 1 over negative 90 degrees. From there, just remember, for all the real terms, like the ones before the angle, you just multiply and divide as usual. And the nice thing about phasors is when you have an angle, when you're multiplying angles, you just add them. When you're dividing, you just subtract. So hopefully, when plugging into the calculator, we should be getting sorry, my bad. Yeah, and also, sorry, I might have put the wrong value for R, but that's 1.58, but we should get 1.26, so that's just me multiplying and dividing the real terms. Then we have 0 plus negative 90, subtract negative 18.43, so that should give us negative 71.57 degrees. So you can just plug that in. It asks for phasor format, so that's nice. Voltage across the resistors, same principle. That's the current is going to be the same times ZR. So again, this will be 0 degrees. For ZR, we had just 1.5. So that is the same thing as 1.5 at an angle of 0 degrees because there's no J. Again, I leave it to you all to just check this with the calculator, but you should get 1.9 an angle of 18.43 degrees. Yeah. Same thing with inductor. That you would multiply by, so for the inductor you had J times 0.5. That's the same thing as 0.5 with an angle of 90 degrees. And sorry, it looks a bit messy over here, but hopefully you all get the point. Just try to keep everything in phasor. When you see a J means positive 90 degrees, minus J means negative 90 degrees. And for VL, you should get 0.63 at an angle of 108.5 2.43 degrees. So in short, this is just like because we saw stuff in series, voltage division should come to your mind. And when you're finding impedance, you can just add them up as if they were resistors. But remember the individual formulas. For resistance, it's just R. For capacitors, it is 1 over JWC. For inductors, it's JWL. Add them up, keep track of the signs, and as long as you're careful, you should be able to get the answer. And for voltage division, you're just setting an expression for I based on the total voltage, the total impedance, and you use that expression for I for all the individual voltages. Yeah, hopefully that makes sense, but are there any questions? So how do you get I? Like remember at the beginning, we just set an expression that Vs is equal to I times Z equals. So for Z equals, we did all the math to find it. For Vs, they gave us what Vs was, 2 cosine 5t. So if you remember this stuff from the phasors, because it's basically like this, it's the same thing. So our angle is, yeah, for our voltage, our angle is 0 degrees. That's 20 degrees. You find Z equals first, do all the math for that, and that's your expression for I. So like for all 3 examples, the capacitor, resistor, and inductor, this was basically I. Does that make sense? All right, thank you. And in the past days, this question has shown up, and especially since it tests like both complex numbers and voltage division. So please practice it. I know it's like a lot of messy math, but practice using the calculator you're going to use for the test. Classmate will help you. And a power question.
Right, we have 2 more questions. This is one of them. So you'll very likely get a power question on this exam as well. So we have an example here. So we're given this circuit here with 2 resistors that are parallel to each other, and we're given a current source. So we're trying to find the power delivered by the source and the power consumed by R2. So we're trying to find 2 different things here. A very important note that you need to keep in mind is that if you're being asked about the power delivered or supplied, then your answer should be negative at the end. You should not be getting a positive answer. And your power consumed should always be positive. If you don't put a negative in front of your answer for the power delivered or supplied, then it will be counted wrong. So make sure you keep that in mind. So for the first part, it says the power delivered by the source. So to do this, let's just write down what we're looking for. Delivered by source. So we're going to use P equals IV, which is equal to I squared over R. So these are all equivalent forms of each other. We're going to specifically use I squared over R in this case because we don't have a voltage source. We just have resistors and a current source. If you don't know how to get this equation here, it's just Ohm's law. You can easily derive it to understand it. So first, because we're looking for the power delivered by the source, we're looking at the entire circuit as a whole. So we need to find our equivalent to be able to plug that into this R value here. So because R1 and R2 are parallel to each other, we do the parallel combination for resistors. In this case, I'll use this form of combining them just so you guys are familiar with it. Because like I said, I think this is easier to do on the exam with your calculator because it's more foolproof. So this would equal 240 ohms for your equivalent resistance. So we just combined R1 and R2 in parallel. So we did 400 times 600 over 400 plus 600, which gives you this value here. So now we have the R that we need for this equation here. So now it's just plugging into this. So it's I squared R I in this case is 0.022 amps. So we do that. We square it and then we multiply that by 240 ohms. And that gives us, also, again, like I said, because it's delivered and supplied, we put the negative out here. Don't forget that. So we get negative 0.116 watts. So this is the first part of the question. This is the power delivered by the source. Again, we're finding the equivalent resistance because the question is asking for the power delivered by the source for the entire circuit, not just for a specific part of it. So next we're being asked the power consumed by R2. So here we need to do current division because we're trying to find, again, we're going to use this equation I squared R, but here the current going in here and the current going into this resistor are different. So we need to do current division so we find what's going into this resistor here, and then based off of that, we need to find power. So to do this, let's just say current division for R2. So we get 400 on the numerator, and we do 400 on the numerator because we're trying to find R2, so we put the resistor value of R1 on top. On the bottom we have 400 plus 600, so the two resistors added together, and then we multiply that by the current source, which is 0.022 amps. When we multiply that through, we get 0.0088 amps. So that means 0.0088 amps are going into this resistor right here, into R2. So now that we have that, again, we just use the power formula. And this time we're going to be using this current. So not this one. We're not using this one. So we do 0.0088 squared times the resistor value of R2, which is equal to 600. So we multiply this by 600, and we get 0.046 watts. Here our answer is positive because this is the power that's being consumed, but here our answer is negative because it's the power delivered. So positive, negative. Make sure you know this. Okay, any questions? Why is the numerator 400 and not 600? Okay, so remember we're looking for the current going through R2. When we're doing current division, we put the value on the numerator is the value of the resistor that we don't want. So it's kind of like the opposite of voltage division. In voltage division, if we were looking for the voltage across R2, then we would put R2 in the numerator. But in this case, because it's current division, we put R1 on top. Okay. Since you said, oh, I think you understand. And if there are no more questions, I'll move on to the last question. Okay. I forgot to erase my work here. Don't look at this, guys. Okay, let's solve this one through together. Ignore what you just saw. So here we have a KCL question. KCL, remember, is the sum of the currents going in is equal to the sum of the currents going out. So we're given 4 nodes. We have A, we have B, C, and D. So what I like to do with questions like this is I first like to write my equations for each of the nodes, so each of my KCL equations, and then after that it's just a matter of solving those equations. So let's look at node A first. Node A is the one right here. So we have I1 coming into the node, so we get I1, and then we have IA and IC coming out. So we get IA plus IC. So we look at this formula, we have the current going in, which is I1, and it's equal to the sum of the currents coming out, which is why we set it up like this. This is for node A. Next, we write the equation for node B, which is this one right here. So let's just erase all of this. Here we have I1 coming out, IB is coming out of the node, but I2 is going into the node. So we do I2 is equal to IB plus I1. That's our second equation, and that's for node B. So now let's look at node C. Node C is this one right here. We see that I3 is coming in, I2 is coming out, and ID is coming out. So we do I3, which is coming in, is equal to I2 plus ID. Now we just have the last node, which is node D. Here we have IC coming in, I4 coming in, and I3 coming out. So we do IC plus I4, since those are both coming in, and then we have I3 coming out. So these are the four equations that we get from the circuit. Now we need to plug in what we are given here. So we're given I1, I2, I3, and I4, and we're trying to find IA, IB, IC, and ID. So we plug each of these into these equations, and then we solve through. So let's see which one would be best to solve first. So because we're given 2 and we're given 1, we can solve for this one right here, for IB and node B. So we plug in 5 into I2, we have IB plus I1, which is negative 0.5. So IB is equal to 5.5 amps. That's the first one. Here, we again have only one unknown, which is ID. We know I3 and we know I2. So plugging in our values for those from what we have up here, we get 1.9 for I3, which is equal to 5 amps for I2 plus ID. Solving this through gives us ID as equal to roughly 2 amps. Wait, hold on. 1.9 minus, yes, that should be negative 3.1. Sorry, I was looking at the wrong thing. Node C. ID is coming out. Yeah, I think I miswrote this on mine. The ID should be equal to negative 3.1 amps. Okay. Now we're looking at node D. So we have IC plus I4, which is equal to negative 0.1. So negative 0.1, and this is equal to I3, which is 1.9. So solving this through, IC is equal to 2 amps. And now using this value here, we can solve for IA in node A. So we have I1 given to us already, which is negative 0.5. We don't know IA, which is what we're looking for, and we're given IC right here, which is 2. So we do plus 2. Solving this through gives us negative 2.5 amps for IA. So to sum up, IA is equal to negative 2.5 amps, IB is equal to 5.5 amps, IC is equal to 2 amps, and ID is equal to negative 3.1 amps. Hopefully, if I don't have any calculation mistakes here, that should be correct. And it is normal to get like these negatives in front of these for these currents. So if you do get a negative, don't make that into a positive. Don't change your answer. And that's that. This was our last question. And we just want to go over one concept really quickly, and then we can end after that. You want to write it here?
Yeah. So there's probably going to be a multiple choice that's about the Eli the Iceman thing, which is the memory thing to remember.
If you swipe over, you can get a new.
Okay, yeah. So the vector for the phasor character for voltage is E. So E is equivalent to the V magnitude of 5V. Just remember that. So it's the phasor of voltage in terms of this equation, but y'all really don't need to know that. But that's why the Eli the Iceman works, because for capacitors, your current leads your voltage, leads E. So current leads the it's in front. So if your phasors, your current's going to be here if your voltage is there, even though that'll be 90 degrees. But and it's the opposite for inductors. So your voltage E leads your current I. Is there any questions?
No, not right now.
Okay. So if you, that's how you remember it. And remember that the angle for an inductor is going to be pi over 2, and the angle for a capacitor is negative pi over 2. And that should be it for that concept.
Yeah, and you guys will have multiple choice questions on there, most likely because the past exams did. So to study those, I would say just go over your reflection questions because they're very similar to those. So if you understand this question, you should be fine for the multiple choice.
Okay. There was. Wait,
You
how
can
do you
just
add a new
swipe
page?
over.
Oh, okay. I believe one of you just asked like a homework question, which might be good for all of you to notice since it can be an easy way to make a mistake. I'm just going to write it down. So this is what the problem says. And that's for amps. So IS is equal to 15 cosine A pi t plus 25 degrees. It gives us that A is 23. And they give us a time that's 2 milliseconds. And they want us to calculate IS when at t equals 2 milliseconds. So, and I'll be honest, I made this mistake too the first time. You might be tempted to do this. 15 cosine 23 pi. You might be tempted to just plug it in like that, but the answer is not going to be correct because you need to pay attention to this. The 23 pi, 2 times 10 to the negative 3, you might have noticed there's a pi in it. That's usually a sign that it means it's in radians. Now, we do have a 25 degrees here, and that means we cannot add radians and degrees together. So a quick way to do this is first calculate what 23 pi 2 times 10 to the negative 3 is. So that should be around 0.1445. Now we need to convert that to degrees. So to convert to degrees, you just multiply by 180 over pi. So that should give us 8.28 degrees. So from there, we can say it's 15 cosine 8.28 plus 25. And be sure, like when you're using a calculator, that it is set to degrees. If it's set to radians, it's going to say something else. But when you do that, we should get 12.539 amps. So hopefully this makes sense. I feel like it's something which, like, if you forget about it, you can. It is wrong. Then you'll get a totally different
I
answer.
have another thing that I can show them actually. So for if you have a hard time with the whole arctan concept, whenever you're converting into a from phasor from rectangular, what you can do is the arctan of y over x also equals arcsine, but it is arcsine of y over r, which r will be your z. So if you do arcsine of the magnitude of the impedance, so the number here over your y value. Oh. It'll of z over y essentially also equals the same angle. But it will never be flipped because arcsine's domain is here. So it always has a unique solution. So it can't repeat itself. Did you already do the frequency thing? Oh, another thing. So if they give you like say 120 volts at 60 hertz, they give you that and they expect you to make a function. So the standard formula for a function, you can just choose your own function. It's gonna be cosine omega t plus your angle. If they don't give you an angle, ignore that. But basically, so what hertz, all you have to do to find omega is multiply your hertz by 60. So you'd be left with a function of 120 cosine of 120 pi t would be your voltage for that.
Yeah, hopefully that all makes sense. It's just like a quick review of concepts you might be using. So, also for the person who asked this homework question, does it make sense? Or if any of y'all have any questions, please let me know.
Yeah, it makes sense. Thank you. And I just had one question. So on the exam, the whole time we have to be in degree mode, right? On the calculator, never in radians.
I think it's degrees.
If you only do degrees, yes. But if you use cosine with the omega value, then you have to use radians. But other than that, use degrees.
Yeah, and as you notice, like the exam should be in connect, right? So when you enter in angles, it almost always asks. I would say it always asks for it on degrees. So at the end, be sure everything is converted to degrees.
Okay, got it. Thank you.
Yeah. So like in the problem which you just sent, the most likely issue was because I was like trying out different values. It seems like you just plugged it in straight up and that gave a different value. So the 23 pi t, that is actually the same thing as WT. So W is always in radians. So just be sure all of you keep track of that and ensure that it's all converted to degrees at the end. So please let us know if y'all still have any more questions.
I have. I'll be in that for tutoring between 1 and 2:30. No, 2 and 3:30 today. If anybody has questions.
Yeah. So one of our tutors, actually, can you just state your time?
Okay. What's the? So I will be in the IEEE office today between 2 and 3:30. So if y'all need any if you need any questions answered like in depth, I'll be available.
And I'll be there Wednesday from 10 a.m. to 12 p.m. So I think the exam stretches till Wednesday. So if you're taking it in the evening, you can come by on Wednesday.
Yeah. And as always, like if you wanted to share a specific question, be sure you can use the tutoring channel as well. And I just have a few quick tips for the exam. So be sure you list out all your steps because there might be partial credit. And even if Connect gets it wrong, it doesn't always mean the end of the world. And Connect does have a tolerance, like a 1 to 2% tolerance, but to be on a safe side, if you can, write down as many decimal points as you can when you do each step and write it down. So that way you're not getting incorrect answers because you accidentally rounded up or rounded down something.
One thing, so when you're doing your calculations, try to do as much as you can in the calculator, because then you can use the like, the like answer. What I don't know how it is for Casios, but in TIs, you just keep everything in that answer, and what that does is it keeps like 13 decimals, because I know of many people that have missed a whole problem because they rounded.
Yeah, that's
Because if there's a lot of steps, you have to keep those decimals because it's not sig figs. You have to be exact. And if you can, use fractions, but a lot of calculators don't help. You can help with
So yeah, like what he said, just try to save values in your calculator so that way you're not actually rounding up stuff. But I would still like write your steps down just so you keep track of what you're doing. And
Yeah, everything.
yeah, every single step, just write it down.
Yeah, and I took this class last semester with Dr. Abulaiha. I feel like they're good with partial credit. I think they're nice with it. So yeah, if you do have your steps down like they said, you should get a lot of credit. So you'll probably be fine. But yeah. Good luck. You guys are gonna do great. Good luck.
Yeah, you'll all do great. Don't worry too much about the exam.
You're welcome. If you stuck this far. Ooh.
Yeah, and okay.
Okay, I think everyone
Yeah,
left.
okay.
All right, in that case, bye. Good luck again.
Okay. So you wanna
I can end it from here.